Okay, we're going to talk about air pressure this week. Uh, we've dealt with getting energy into the atmosphere, which influences temperature. Temperature directly influences air pressure. Why would air pressure be important? Why would I care about air pressure? It's not something you literally think about as far as when you're looking outside at the weather. You don't think, oh, the pressure's high today. That means something. No, you think it's raining or snowing. Well, air pressure has a significance. It controls, actually demonstrates where there's low pressure, which we know means rain coming in, and it demonstrates where there's high pressure, which typically means nice weather. So air pressure is important. It also helps to influence where air is going to move because there are variations in air pressure. So we'll talk about some of that here a little bit. So what is air pressure first? Well, believe it or not, you're weighted down every day from the force of the air. And force is just the mass times acceleration. So mass is so many molecules in an area. Acceleration is just how fast they keep moving faster. So when you push the gas on your car gets moving faster. That's an acceleration. Well, guess what? Molecules do that too. And when they hit each other, they exert a force. And that total air pressure is the force of all these collisions. So we know the atmosphere is made up of different gases. Well, if you total all the gases up, you get an air pressure. Each one of those gases has an individual air pressure. So in other words, if you took the pressure of oxygen or you took the pressure of a water vapor, add them up and you're working your way to the total air pressure of the atmosphere. And air pressure depends on its mass, and molecules we know have molecular kinetic energy. So, but you know, you can register in a way by temperature by using the Kelvin scale. So the thought of the weight of the overlying area. So weight is that force, which also includes gravity, pushing down on a mass. So the more density, more molecules, the bigger the mass. And the average sea pressure, level pressure is basically 14.7 pounds per square inch. Think about that on your body. You have 14.7 pounds every square inch weighing you down today. So one day you can stand up, right? All structures do too. But guess what? Air is inside every structure and inside us, so that it's all pushing back as well. So that's why we don't get affected by it. Barometer is how we measure air pressure. There used to be a lot of mercury barometers around, and they discovered mercury was bad for us. So they've gotten rid of almost all of them now. Matter of fact, the Weather Service is, I think, completely done away with them anywhere they take weather observations now. And these are the different units of measure. Almost all of you are interested in, or listen to interested more of inches of mercury. Because as old scale barometers we used to have, all measured inches of mercury. And we are an English country as far as the standard system of measurement goes. We're not metric. However, meteorologists are metric. So that means we're going to probably look at things as a millibar instead, or a kilopascal, which is just a metric unit of pressure. So, which is exactly the same as a millibar in essence. 1,000 kilopascals is the same as 1,000 millibars. So, what you're going to hear, though, from most TV meteorologists is that pressure is in inches of mercury. So they're going to try to tell you that. Because guess what? At your home barometer, it's almost always going to be measured in inches of mercury if you have one. Now, interestingly, air is different than other fluids. We deal with air as a fluid, but it's a compressible fluid. What does that mean? Well, if you put air into a bottle or into your tire and start pumping air into it, more and more air can continue to go into that tire. That means it's compressible because it's getting compressed together. The molecules are getting pushed tighter and tighter together. Now, you try to do that same with water. Take a hose of water, stick it into a bottle, you fill the bottle to the top. You ain't going to get any more water in there. It's not compressible unless it has extreme pressure. So air is. So that's why as you go up in the atmosphere, there's less air because it's all been pushed down towards the ground. It's been compressed down to the lower part of the atmosphere. And somebody through the years has measured the standard atmosphere, which is the state of the atmosphere averaged over all latitudes and all seasons. It's just a vertical scale of how the pressure, temperature, and all change. Now, horizontal air pressure, we've had questions already where I ask you, if a cyclone is approaching your house, what happens to air pressure? Well, a cyclone is low pressure, so air pressure is going to drop. Take a look at this. This is a cyclone approaching somebody's house. Look at the air pressure. It starts out 10, 11, 10, 13 millibars almost. Where does it get down to? 1,007, 1,008 millibars. There is low pressure that went by this place during this time. It approached here as the pressure was dropping, and it left here as the pressure now begins to go back up and high pressure is beginning to move in. So there are precessions of these air masses bringing these changes in pressure, and that brings changes to the weather. Weather becomes stormy when air pressure falls. It clears out when air pressure rises, typically. So why? Well, let's think about how pressure can change. One of the reasons pressure can change is air temperature. Air temperature in the atmosphere. The hotter the air is, the more kinetic energy those molecules have. They're going to hit each other and they're going to push each other apart. So you have less molecules in a given area, which means the density is lower. Lower density is just how many molecules you have for a given unit of area. So the less molecules that are there, the less density you have, and guess what? Gravity is still the same. So you wind up not having as much air pressure where the air is hotter typically. Interesting, considering we get high pressures in the wintertime, very cold air masses. But then in the summer, we also get high pressure that are fairly warm air masses. However, the difference in pressure is relatively significant. The millibars of maybe a wintertime cold air mass might be 1040. Maybe the summertime, warmer but still high pressure, might be a 1010 millibars. That 30 millibar difference or so makes a difference in the amount of molecules that are there. So air pressure can drop much more rapidly with altitude in cold air. Well, think about it. You have a whole bunch of molecules brought together, very dense in cold air. So if you move through that cold air into vertical, you will find the density that the air is getting pushed apart more and more, so this pressure drops fairly quickly in cold air. So you wind up with actually low pressures above this very cold air mass at the surface many times. Interesting reverse concept there. 500 millibar surfaces represent about halfway through the atmosphere. So at a lower altitude in colder air than warmer. So in other words, we've been talking about the jet streams in the troposphere here. Yeah, we're just verifying what we've been trying to talk about with the tropopause. The tropopause goes lower near the poles, higher near the equator. Here is your explanation for that. The more heated air pushing the molecules apart, the higher the tropopause is going to be, which is going to be near the equator. The colder, the denser the air is, the lower the tropopause is. And finally, guess what? Muggy air, which we all hate to be in, it feels very oppressive and heavy, is actually less dense. Water vapor is less dense than normal air. So when you have a very humid atmosphere, you actually have less density to the air. All right, because the air is a fluid, if you do something to one part of the air in a column, you're going to have an impact on the other part. So if air is converging, which just means air is coming together, like just clapping your hands and pushing the air together, what happened to that air? Well, in a column, if you're doing it towards the top of the atmosphere, the air is going to want to come down. So it's going to come down, hit the ground. Well, if it hits the ground, it has no place to go, so it's going to diverge. It's going to blow apart. So if you have convergence aloft, you'll wind up typically having divergence below it. Guess what? Divergence means you have sinking air, you're pushing more molecules there, you're typically having high pressure. The ideal gas law. It's a great way if you need to know pressure, temperature, density. If I know 2 out of the 3, I can determine the third. That's all it is. They're all proportional to each other. So we know air cools when it rises. We know it warms when it sinks. Why is that? Well, here is a reason. If the air is compressed, energy's got to be used to push those molecules together, right? So if that energy is being used, it's being absorbed by those molecules. What happens is the temperature rises. You're getting those molecules to move faster and faster. Now, if the air expands, as you go up in the atmosphere, then it's getting pulled apart. You wind up with energy being used by the air. So the air is cooling. So these are energy processes that actually impact temperature. You drop air down in the atmosphere, it's getting compressed, it's going to warm. You take air up in the atmosphere, it expands, it's going to cool. And since we can know this and actually calculate this expansion or compression, we know that if there's no moisture in the atmosphere, moisture is a different column, different thing. We can come up with what we call an adiabatic process. And I kind of brought that up when I talked about temperature last week, maybe a little ahead of this. But basically what happens is as you go up in the atmosphere, air cools about 9.8 degrees Celsius per 1,000 meters. So if you go up a mountain 5,000 feet high, you have cooled about 5.5 degrees Fahrenheit. You go up 2,000 feet, you've cooled about 11 degrees Fahrenheit. But this is if it's a dry air mass. Now, moisture does something. We know moisture has latent heat associated with it. So if it's evaporating, it's cooling. If it's condensing, what's it doing? It's giving off latent heat. So if it condenses, then that lapse rate changes because some of that latent heat went into keeping the lapse rate up. That's why a moist adiabat, the moist lapse rate, when you get into a cloud, is going to be different than the dry adiabatic lapse rate. And you're going to love all the discussions about that we're going to have in the next few weeks. So with that, I just wanted to take a quick peek as to what's happening today. All right, just quickly. Here should be coming up. Yep. We have a cold front that went through Ohio and part of West Virginia overnight. Not the most strong cold front in the world. Matter of fact, high pressure is only 10, 12 millibars. Not really high. Millibars here for the low is only 1,005. And out ahead of this cold front, 10, 12, I have a 10, 12 here. So this cold front's not going anywhere. Pressures are about equal. Nothing significant is happening here. But let's take a look at Parkersburg. What I wanted to show here, this is a relative humidity and temperature and dew point and all that. But let's just take a look at pressure. Sea level pressure. What happened? Well, here is the current air pressure. 1023 on the 17th. Here's the 20th. Here's now. Air pressure is starting to rise here. Right here is when it reached its low. Well, if you go back here on this little map, you'll notice that this cold front was approaching them then. So this relatively small change in pressure indicated the cold front was moving towards them. Now, as the cold front passed them, pressure has been going back up again. Not a big deal. It's not a major front, major piece of weather, but it is a cold front is going to be accompanied by lower pressure with it, as is a warm front. So when they move through your area, the pressure is going to tend to drop, and when they move away, pressure is going to tend to increase. And you can see this. And I wanted you to think about this. Think about the vertical now. We have talked about how pressure goes down, goes up into vertical, it goes down, excuse me, very quickly. Well, if I go in the vertical, 850 millibars, which is, we'll say 1,000 millibars is roughly the surface. So that's 150 millibars up. 850 millibars is only maybe 5,000 feet up, 1 mile. So in 1 mile, I've dropped 150 millibars. Look at this. This never does that in the whole time. So the surface air pressure doesn't drop like that. Yes, it drops more in a hurricane. There's a nice Hurricane Fiona right now, I can show you, that is has become a major hurricane as it's hitting Turks and Caicos. And the pressures there are probably dropping at the rate in an hour of maybe 9 to 10 millibars an hour. And that is a significant pressure drop. But that is nothing like what's going in the vertical, just walking up into a mountain. So hope you got a little bit about this and why pressure is so important. So let me know if you have any questions.